Let's get started with a bit of an introduction to gated fast sCMOS technology. So I'm going to run over just the basics of intensified camera operation, sort of the key components and some of the considerations we need to take into account. Sensor choice, CCD versus sCMOS, global versus rolling shutter, the pros and cons of each of these and why we've chosen global shutter over rolling shutter for the iStar sCMOS. Then I'll talk a little bit about sort of getting the most out of the sensitivity and dynamic range of the camera and the noise source considerations that we need to take into account with these cameras. And then I'll talk about some of the sort of common blemishes and artifacts that you see in these cameras and how we sort of can mitigate those. And then I'll have a brief sort of talk about timing diagrams and the sort of timing considerations you need to take into account for situations where you have the camera acting as the master or the camera acting as the slave. And that should hopefully give us enough to talk about. So without further ado, the basics of intensified camera operation. So as you may be aware, intensified cameras sort of all came about through night vision technology. As they were developed for, intensifiers were developed for extremely low light imaging conditions, for instance, surveillance. And it was a way of going from a sort of a low photon environment where you didn't have very much signal or much visibility to being able to apply a high gain to that to multiply up your incoming photon and get much more signal. And the way image intensifiers work is they're able to amplify a single incoming photon, and they then turn this incoming photon into an electron. This is then channeled into a microchannel plate, which then multiplies up this single electron through impact ionization. And these multiple electrons then impact with phosphor screen, which then produce many photons, and hence which are much more detectable than the single incoming photon, and hence we get an amplified signal. Well, it's a little bit more complicated than that because there's many components that make up a gated camera. So if we were to take sort of the front end of one apart, we've got several main components and considerations. We've got firstly the input window, which can be sort of the ultimate limiting factor on the detectable wavelength to some degree, and upon that, photocathode substrate is laid. We then have the photocathode material itself, which converts incoming photons into photoelectrons. This is also a gateable structure, so you can effectively open and close it using an electronic signal. And I'll talk a little bit more about that in a minute. And then we have behind that the microchannel plate, which amplifies up the photoelectrons through impact ionization. And then behind that, we have the phosphor, which then converts these photoelectrons, as I mentioned before, into visible photons. And then we have an interface between the phosphor and the sensor. And this could either be a fiber optic interface or a lens coupled interface. And I'll talk about the relative pros and cons of each of these later on. And then we have this then connected to our two-dimensional sensor, which could either be a CCD or an sCMOS sensor, depending on what we're trying to do and trying to achieve. And I'll talk about the relative pros and cons of each of those as well as we go along. So I thought I'd start at the front and work our way towards the back. Like the input window that you have on the camera, this, as I said before, this defines the lowest detectable wavelength by the intensifier. Gen 2 photocathodes are deposited on silica, so this then means you can go down to as little as 125 nanometers if you're using magnesium fluoride. Or Gen 3 photocathodes are deposited on glass due to there's some constraints in the actual manufacturing due to thermal expansion. So this tends to limit Gen 3 photocathodes to around 300 nanometers as far as the lowest wavelength goes. So of these materials that are then deposited onto this glass, you have a choice of photocathode materials. And Generation 2 photocathode materials are multi-alkaline materials. And as I said before, you can put these inferior onto magnesium fluoride. So you can actually go down as low as 125 nanometers. In terms of wavelength, they have a sort of maximum quantum efficiency of around 25%, and you can gate these down to hundreds of picoseconds in terms of time. But it does need a metallic underlay to achieve fast gating, which can impact the quantum efficiency somewhat. And secondly, there are Gen 2 photocathodes, which, as I mentioned before, these are then directly deposited onto glass, which then limits their wavelength range sort of down to 350 nanometers. But these don't require an underlay, so they can achieve fairly good quantum efficiencies in some regimes, and they are again gateable down to hundreds of picoseconds. And it's also possible to have in-gas photo cathode materials, which then can extend your sort of near infrared detection up to over, you know, what 1,100 nanometers. However, the quantum efficiency of these can be relatively low in terms of it's about 5%. So in summary, Gen 2 allows you to go to lower wavelengths, but the quantum efficiency you're looking at is around 25%. Gen 3 is more limited in its wavelength, but you can get higher quantum efficiencies up to say 50%. Whereas InGaAs has a relatively low quantum efficiency, but you can really get towards that sort of near infrared regime of the spectrum. But they're a bit more limited in terms of the gate speed that can be achieved. So in terms of actually how a photocathode actually gates, we achieve this gating by pulsing the voltage in the photocathode. So when the voltage is set to 0 volts in the photocathode, photons can impact our photocathode and generate photoelectrons, which can then be channeled into the microchannel plate. However, what we can do is we can then toggle this and run a voltage across it. And if we put a voltage across it, this actually then deflects these photoelectrons from getting to the microchannel plate. So we effectively can shutter our image using the photocathode. We can effectively shutter our image through this this pulse voltage, which is primarily why we're using them, so we can achieve this really fast time gating. But there's one thing worth noting about photocathodes, and this might be something that you come across if you try and gate to very short time frames, is that these photocathodes have a very finite conductivity. So it actually takes time for the electrical pulse to travel from the edge inwards into the photocathode. And this can cause an effect, sort of an irising effect, in that it takes a little bit of time before the photocathode is completely open or completely shut. And so this is something worth bearing in mind when you're, taking your images, etc. So what we can actually do is we can actually look at this in reality and see how this actually affects the intensity of the photocathode over time relative to the edges of the photocathode to the middle. So one of our engineers had a look at this. One second, I'll just get the pointer. Had a look at this, and what you can do is you can see that if you see the bottom bar here is time. Over time, you'll see that the left and right edges of the tube, the outer edges of the photocathode, will reach a high intensity of light much quicker than the center region of the tube. So you have a lag between you starting to open the photocathode and your center fully opening. And then the same is true when you then go to close the photocathode. There's a lag then relative to the edges of the tube and the middle of the tube in terms of the intensity that you're still receiving. So that's just something to bear in mind, and it could be an effect that you may see depending on the time scales you're working at. But it's just something worth bearing in mind. Thirdly, behind the photocathode, we have the microchannel plate, and this is primarily used to overcome the sensor noise floor. So the microchannel plate works through the incoming electron, going for a series of impact ionization events to then multiply up the number of photoelectrons from 1 to hundreds or thousands, etc. And this then can effectively be used to detect up to single photon events. And sometimes people actually you can buy intensifier tubes which have dual microchannel plates in them to get even better discrimination of single photon events. But as you can see here from the right hand side, you can go from a 1 times gain where you can't discern a single event up to a 500 times gain where you can relatively clearly see each of the individual events that have occurred within the system. One thing I think is worth really mentioning though is that these photocathodes can be susceptible to sort of UV photons going straight through them and directly interacting with the microchannel plate themselves. So if you're taking a long exposure or an exposure and you're gating your photocathode, what you might see if you're working near the UV is actually that you're getting some signal even when it's shut, because of the shuttering efficiency isn't very great. Isn't quite as efficient in the UV sort of region. So one way of working around this is that we have a function on our intensified cameras called IntelliGate. And what this does is it turns the microchannel plate off between gates. And what that does is that actually helps to boost your rejection efficiency during the sort of time when the gate is off, to basically have a better shuttering efficiency. Now this is limited to 5 kilohertz, but I think it's just worth noting that that's a feature. And if, for some reason you're gating, you're seeing some signal for some reason, if you happen to be working in this regime, it's worth noting that this is an option and a way of mitigating this potential problem if it does come up. So behind the microchannel plate, we have obviously our phosphor screen that's converting our electrons back into visible light that our sensor can detect. And typically this converts these electrons into green photons, which best match the quantum efficiency of the sensor. Hence why night vision goggles, etc., are all green. And the most common phosphor that we tend to use is P43, and you can see it in this peak here. And we also use P46 in some instances as well. And just to go into that a little bit more, the reason you may use P46 over P43 is that P46 offers a faster decay time than P43. So for applications where the decay time can be an important factor, say beyond 300 hertz in terms of repetition rate, then we'd recommend P46 or into frame time, etc. So by decay time, what we mean is the time it takes the relative intensity of the phosphates to return down to 10%, as you can see here on this graph. But there is a trade-off, though. Like you would think, oh, okay, well, why don't we just use P46 for everything? P40, yeah. The reason for that is basically between P43 and P46, there's some trade-offs. So P43 is, if you imagine that the relative intensity is 100% at P43, if you use P46 for the same application, you would only get 30% of the relative intensity. Also, because the phosphor itself in P46 is a bit more granular than, or has like larger grain size than I think P43, what that then means is that actually limits your resolution slightly relative to P43. So you get a 30 micron resolution limit as opposed to a 25 micron resolution limit. So hence, there are trade-offs if you have to use P46 as opposed to P43. Hence, we try to steer people towards P43 if it's the most fitting thing for their particular application. If you're not going to go down to these really short interframe times of say 200 to 400 nanoseconds. And then obviously behind the phosphor we have it then coupled to a sensor, and there's two ways we could have done this. We could do this using either a fiber optic plate or using lens coupling. Now we opted for the fiber optic plate for several reasons. Firstly, because with a fiber optic to phosphor couple, you have a much higher throughput, so you're getting the most out of all your signal. It's also very compact, so you can actually have a compact camera as opposed to a camera with a big lens coupled to a microchannel plate, etc. And the one trade-off here is that you do get this low contrast pattern from the fiber optic interface. And I'll talk a little bit more about this as an artifact later. But what's good about this is you can at least background correct this. So if you take a background image of this pattern, you can actually subtract that from your image and mitigate that. Whereas if you had a lens setup, in theory, with a lens setup, you would actually get the best spatial resolution. But with an intensified camera, the problem is actually that the photocathode itself tends to be the sort of resolution bottleneck that you have. So even though you would get better resolution with a lens coupled setup, you actually wouldn't gain that benefit. So there's not really a benefit there. You also risk getting some kind of image distortion or vignetting, so darkening of the corners of your image because of the optical setup. And you also have a larger camera. So hence we went for a fiber optic plate in the end because it seemed like the more logical design choice. Now, so you're coupling, you've got your whole system and you're coupling it into your sensor, and then you have a choice to make of, well, what should my sensor be? Should it be a CCD sensor? Should it be an sCMOS sensor? Well, just for those of you who maybe aren't as familiar with CCD detectors, just to give you a brief overview of how they work, how sCMOS detectors work. So a CCD detector, relatively simple. You have a series of pixels, and your photon falls onto a pixel and generates a photoelectron. And then this photoelectron is then transported down into this readout register and then into a readout node, which then converts it from analog into digital. And these can basically read out one pixel at a time. You could have maybe multiple readout registers, but you can be quite speed limited in terms of these. But what you can do, so also what I think is quite a good way of actually thinking about how the CCDs work is, I quite like this sort of diagram which shows it as buckets, in that if you imagine each pixel as a bucket with raindrops of photons falling on them, and then you've got buckets full of electrons, you're then shifting them down to your register at the end, and then reading them out into the main bucket at the end, is maybe a nice simplistic model of understanding this. But yes, one thing you can do with CCDs that you can't do on, for instance, sCMOS, etc., is you can bin multiple pixels together, or bin a whole row. And by binning, I mean merging together into like a whole row, and so you can achieve fast speeds, etc., which is useful for things such as spectroscopy. So if you were to compare, so in short, if you have a CCD, what you get is it's relatively slow, but because you can bin whole rows together, you can get very quick rates for spectroscopy. And you can also deep cool it to very low temperatures. So for spectroscopy applications, CCDs can be quite a good one because you can get, good multi-track spectroscopy frame rates. You can also do imaging, but just at a few hertz frame rate, which may be fine for some applications. Whereas in a sCMOS technology, you sort of have this, but you've miniaturized it into each individual pixel. And instead of reading off one pixel at a time, you read off entire rows at a time. So what this gives you is, so you have this array of photodiodes and amplifiers together, and this means by being able to read out full lines simultaneously, you get much faster frame rates relative to CCDs. So it's much better when you're taking a whole image as opposed to, a small a line, etc. So this is also one thing that I should maybe point out as well, is that with a CCD, if you go faster, your read noise increases. Whereas with a CMOS detector, if you go faster, your read noise stays the same. So you can go very fast and you don't see your noise floor increasing. So sCMOS is very good for full frame imaging and fast multi-track spectroscopy, whereas CCDs are good for fast, spectroscopy and some low frame rate imaging. So there is a place for both of them. It's just worth pointing out maybe the relative pros and cons. Also, I just want to mention, so in the iStar CMOS camera, we've opted for a global as opposed to a rolling shutter, and the reason for this is sort of quite clear when you break it down. So global shutter's got a few advantages. So when you have a global shutter camera, what you have is every pixel is actively exposing simultaneously at the same time. And as you can see from this image on the right-hand side, which is slowly increasing intensity equally everywhere. And then when it stops acquiring, it all stops simultaneously. Now, this is very important because if you're trying to use it for an application such as say, PIV, like PIV, where you're taking two rapid interframes, you need all the pixels to stop and start acquiring simultaneously to actually achieve that. And you also want even illumination of pixels at a given time frame, because what happens is that if you don't evenly illuminate all your pixels at the same time, if you're using a phosphor to acquire images, you'll then see a difference in intensity as you read out and expose, as you would in the case of rolling shutter, where you start acquiring from the middle of your sensor, for instance, and expand outwards. And then once you've acquired the whole image in the center columns of the sensor, you then start reading them out sequentially and then sort of opening the shutter in reverse and then acquiring the next image. So rolling shutter is not particularly good if you have a phosphor gradient, because as you can imagine, you're going to see a different gradient of phosphor intensity across the rows and perhaps within the image. Also, one thing about global shutter is it has you can achieve sufficient speeds for the majority of applications. So you can get up to 50 frames per second with it. So of the kind of applications where this is targeted at, that's actually sufficient for most. Reasons you might have chosen rolling shutter, though, is that you can achieve faster frame rates and you can achieve a slightly lower read noise than global shutter. But because we're using this in conjunction with a phosphor and intensifier, the sort of trade-offs just weren't there. So hence we opted for a global shutter sensor choice in the iStar sCMOS as opposed to rolling shutter. And yeah, as I sort of mentioned before. So I think that sort of goes for every single part of the camera. But yes, so I just want to move on really to, within that, it's then now a question of, well, what determines your sensitivity and dynamic range? What are the factors that affect the quality of the images you're getting? So I'm going to talk about some of the main noise sources that you get within the camera and ways in which, sort of alluded to previously, but I maybe haven't spoken about, ways that then you can mitigate these kind of noise sources. So in terms of where you get noise, the sensor is a big source of noise within the whole system. You've got the shot noise from your incoming photons adding to your noise. You've then got your read noise that you're getting from however you're reading it out. That's just generated through the electronics. Shot noise is through difference in intensity of photons and difference in quantum efficiency, etc. Dark noise is your thermally generated electrons. So dark noise, or dark current as it's often called, is basically over time, if you've got a sensor and you've got it at a certain temperature, over time you'll spontaneously get the generation of photoelectrons within the sensor. So we have to run these sensors, like in the case of CCDs, with using keep clean and sCMOS, using keep clean cycles to keep the sort of dark current noise low. So when you're ready to take an image, it's not present. So that thermally generated electrons, and then there's spurious noise, and there's a few sources of this, but often one you see in particular is clock-induced charge, which is noise that you get when you're moving your photoelectrons through your sensor. So those are sort of the main sources of noise on the sensor. There's also some sources of noise in the photocathode. So there's this thing called equivalent background illumination, or EBI, and this is similar to dark current within a sensor, is the spontaneous generation of electrons, basically due to thermal excitation within the photocathode. Alongside shot noise, EBI is perhaps one of the main limitations in sensitivity that you get in ICDs for applications where, if you're trying to look at ultra low photon fluxes, so say you're trying to do photon counting, etc., EBI can be a real limitation in terms of sensitivity. And the way this actually looks in reality is, if you take a photocathode and you do a longer and longer exposure, over time you see more and more of these sort of dark EBI events being picked up in your sensor and going through the whole system and being multiplied up. So that's one of the sources of noise in the photocathode. So just to sort of summarize those, I may mention a few others that I hadn't. So we covered the sensor noise. You've got the photon shot noise, the readout noise, dark noise or dark current, clock-induced charge noise, spurious noise, and there is also like a pattern noise associated with sCMOS technology that's typically corrected out during the sort of QC stage within Andor. You then also have shot noise in you have photon shot noise in your photocathode. You have your EBI from your photocathode. You've also got photoelectron shot noise within your microchannel plate itself, and then there's also a certain amount of noise from the amplification, because not every electron is amplified equally, so to speak, in your microchannel plate. And then you have a certain amount of noise generated by your phosphor in the amplified photoelectron signal shot noise as well. So there's quite a few sources of noise there, but don't be concerned. There are many ways in which these are then actually mitigated. So how we improve our signal to noise ratio to overcome these various sources of noise. As I mentioned before, microchannel plate gain, we use this to overcome the read noise flaw, and it was very effective at doing that. And then the dark current itself, or dark noise, we can generally minimize this through cooling our sensor. And basically, the cooler you make your sensor, the more you minimize this dark current. Dark current as well, though, tends to be less of an issue, because if you're running relatively quickly, there's not much time for dark current to accumulate. So actually running fast can help minimize dark current as well. And also clock-induced charge noise is actually relatively negligible in CCD and sCMOS, so it's less of a concern. So what this means you can do is, you can have, say you have your CCD or your sCMOS exposing for a millisecond scale. What you can do is, if you have your high repetition rate laser and you have the same event occurring over and over and over again, instead of taking individual exposures and then sticking them together in one exposure, you can have multiple iterations of the same event happening, and you can open your gate for each of these events to build up signal on this single frame, and hence get a much better signal to noise ratio. And yeah, overall what you see is then your counts per per signal per exposure then are greatly increased, and therefore you get a much better signal to noise ratio. So that's one way of increasing signal to noise ratio, but obviously that's dependent on you having a repetitive event that you're looking at. Another point I think is very important, and I think is often not appreciated, is like we're applying this gain to our cameras to increase our, overcome the noise flaw. But by applying gain, we're also actually reducing our dynamic range. So one of the reasons why we've gone with sCMOS technology for high speed applications is that by having a lower noise floor to begin with, you don't need to apply as much gain to actually then overcome that that basic noise floor, and therefore you get more dynamic range. So just to put it into sort of context, for instance, with an iStar sCMOS, if you're binning 2x2, your full pixel read noise is at 5.2 electrons, and your well depth is 120,000 electrons. And if you compare this to, say, interline CCD cameras, which I think they've obsoleted all these sensors, but these have a much higher read noise when you're running it at the high frame rates. So what that means is that you have to apply only 5.2 times gain to an iStar sCMOS to sort of overcome the noise floor, whereas with these you'd have to apply up to 70 and 90 times gain. So though you have more well depth with these cameras, you actually end up with much less dynamic range compared to the iStar sCMOS. So I think it's very important to just take note that by having a low read noise to begin with, it makes life much easier when it comes to then having good dynamic range down the line. So I think that's pretty much all I want to talk about in terms of sources of noise and ways of improving signal to noise, etc. I just want to now talk briefly about some of the blemishes and artifacts that you come across sometimes in intensified cameras. And the most common and easy to see one that I'm sure you'll come across is if you set up your system in a particular state where you're looking at a low contrast image, we have this low contrast fixed honeycomb pattern of across the image. Now you see this actually much more in cameras such as sCMOS cameras, where you have smaller pixels, so you're sampling the fiber optic better. And basically this arises because when they create these fiber optic bundles in these sort of hexagons, and then they actually, through the process of attaching these together, there's then often that it's not 100% perfect. So what you then do is you can actually see this sort of honeycomb pattern in between these sort of fiber optic bunches. But because this is a fixed sort of artifact, what you can do is if you take a background image, you can then subtract this and sort of mitigate it, so to speak. Also, what you might see from here, and yes, so it's relatively low intensity across, if you were to do a line scan across one of these. So also, you can also see the sort of defects where, in particular, at the corners of where these sort of honeycomb things come together, where you also get this slight decrease in the intensity in some instances. And within these fiber optics, there's also these fibers which are called extramural absorbers. They're basically sort of dead fibers, but what they do is they help prevent crosstalk between the fiber optics, and they're randomly scattered within the fiber optic bunches. And sometimes if you're really sampling for small pixel size, you can sometimes pick them up within the hexagons themselves as well. So those are just some artifacts to be aware of, but the fact is you can take a background image to correct for these. So it's not actually a really big issue. Now, this is something that one thing that you can get in intensifiers as well is a sort of a central bright spot. This is typically some kind of a defect within the intensifier manufacturer's process. You see the central bright spot when if you're observing an image of something and your intensifier isn't perfectly perpendicular. What you get is some internal reflection of light within the intensifier. And so what this can then result in is higher intensity of light within the center of the image intensifier. So the best way to mitigate this is typically maybe change your change your incidence angles of the light that's coming into your intensifier, because at higher incidence angles, this kind of effect can be more pronounced. So it's just something worth bearing in mind. So if you see that, you can look to understand where it's coming from and how to maybe try address it. As I wanted to allude to before, one other form of artifact that can occur sometimes in image intensifiers is image intensifier glow. And this is normally a defect from the manufacturing process, either in the microchannel plate, the phosphor, or the photocathode. And these are very hard to detect because often these actually only occur in certain gain or light conditions. So when we get an intensifier from our manufacturer, we do a series of tests to try identify any of these intensifier glow spots, and they typically occur in a fixed point on the intensifier. And what you can then do is you can then pair an intensifier, as we do, so that because we have various different shapes and sizes of CCD and sCMOS sensors, we try pair it such that your sensor, you have a rectangular sensor, you pair an intensifier such that a spot like this isn't detectable or isn't occurring on an image. So typically these shouldn't be things that you come across, but if you do, then at least that's sort of how they can occur. But as I say, we try and mitigate that by how we place intensifiers relative to sensors. So they fall outside the field of view. And lastly, I apologize if I've gone through this quite quickly. I just want to talk about some basic timing diagrams and some of the considerations that you need to take into account with these, because we use timing diagrams as a helpful tool of putting together a series of sequence of events in time. So typically these can be broken down into, it could be internal processes within the camera. So it could be sensor, photocathode gating, it could be an output signal, and there could be an event that this is all relative to. And we basically have a axis of time, and we use these sort of blocks to indicate whether or not such a feature is active or not. So if the sensor, for instance, is raised, then it means the sensor is active. If the photocathode gate is raised, then it means the photocathode gate is active for that particular time width. And so if we take an instance, so there's sort of two scenarios really, which I think are worth briefly touching upon. And we're going to, hopefully in some later sessions, we were going to have some, showing timing diagrams actually replicated on oscilloscopes with an actual setup, so you can see what they look like in reality relative to the theoretical timing diagram. But there's two main circumstances here. There's the circumstance where you have the camera as the master. So the camera is sort of the driving force. It is acting as the digital delay generator and the timing the sequence of events for the experiment. And there's a circumstance where the camera is the slave, and I'll talk about that in a second. But say you have a circumstance where the camera is the master, what you'd have is some kind of internal camera trigger. So this could be someone pressing a button in Solid software or in some kind of SDK that they've linked up, etc. And this internal trigger then triggers the sensor. And because we're triggering it internally, we can make sure that there's no keep clean cycles running or anything else that might delay the triggering of the sensor. And we're using the camera to sort of mark time at the start of everything, and everything happens relative to when the camera sensor starts. So from this, you can then set a fixed delay of your photocathode gate such that it falls relative to the sensor at a time when you're expecting an event to occur. So if I just go forward one more, but you could also trigger an output from the time when your sensor starts acquiring. So this could be an output to go trigger a laser, which then triggers an event which has a certain time delay. And you can then shift your photocathode or your output trigger to then line everything up such that you're acquiring your image during the event as you want to, as desired. And you can use this output trigger because it's sent very accurately to then trigger your event with a great degree of accuracy. Now, I have shown these delays as sort of delta 1, delta 2, as sort of fixed for the repeating unit that comes afterwards. But what you can do in iStar sCMOS software, or the Solid software, in general, is you can set your software such that you could add a sort of a change in time with every repeating sequence. So say you're looking at some kind of transient phenomena that's repeating, you could have your first iteration of so you've got a laser hitting something, creating a plasma plume or whatever at this time, and then you can shift this gate slightly forward in the next sequence by whatever you want it to be, to then witness how it's changed in that next fraction of a second or nanosecond or whatever. And yes, so in general, you have one whole sequence, which I've shown here as an exposure time, but then you have a gap after exposure time, which is your readout time, and then a certain wait time for things such as keep cleans to end, at which point your then next sequence can then begin. So I think I hope that gives a bit of a brief overview of what it's like with the camera as the master. If you've got any questions about this, please let me know. But I'm hoping that in future sessions, we'll go a bit more deeper into timing diagrams and talk about the more sort of complicated instances beyond these sort of simple triggering ones, and sort of things we need to bear in mind with those, because these can get fairly complicated. And this is just the most simple version of the camera as the master. So in an instance where you have the camera as the slave, so we have our timing diagram again, but instead of using the camera and sort of the camera being triggered by the software as the start of our experimental sequence, instead we have some kind of event. So it could be, for instance, the flash lamp of your laser. It's some kind of hardware anyway that is from an external event that is triggering some kind of pulse, which then gives you some kind of external trigger. And this external trigger can then be used to trigger the sensor and various gating and outputs from the camera. But one thing that's, I think, very important to appreciate is when you go from an external trigger like this, you have a delay called an insertion delay between the start of this trigger and the start of, say, your sensor exposure. And this, again, is caused by things such as, your sensor running a keep clean cycle and having to interrupt that to then start its exposure. And what this can mean sometimes is that you have an event, but you then are only able to trigger the camera after that event. So you actually then use the first event to trigger the camera so that it can be exposing during the second event. And similarly to the previous setup though, once you've got this external trigger going into the camera like this, you can then adjust your gate time to image the event, scan back and forth to figure out when your event's happening. And you can then also set an output still. So say maybe after something has happened, you want to change a microscope stage or make it move or something after that, or you need an output signal for whatever reason, you can do that with a set time still off an external trigger. And then again, you can change these delays as necessary, or set them so that in future ones you're then scanning through at the event at a later stage if you're trying to build up a time resolved image sequence of some kind of transient phenomena. So yeah, I think that's about as far as I'm going to go today. Anything else?